Welcome to Lecture 3.3, Proving Universal Statements. I'm beginning this lecture with the same slide that I began the previous lecture with. That was on proving existential statements. And I'm not going to go over this slide in the detail that I did in that lecture. So please go watch that lecture first if you haven't already. So there I defined formally what even, odd, prime, and composite numbers are. And we did thought experiments about what it takes to prove an existential statement, disprove an existential statement, prove a universal statement versus disproving a universal statement. And in this lecture we will focus on these two definitions, prime and composite numbers. The previous lecture we mostly did even and odd numbers, and also proving universal statements, these types. Though we did a couple of these things, we couldn't avoid them. A couple of these came up in the previous lecture as well. And that's because disproving an existential statement is basically proving a universal statement. Recall from the previous lecture that an example of an existential statement typically had the form, there exists an x in U such that Q of x is true. Now you could come up with something like there exists an x in U such that P of x implies Q of x, although that's kind of weird because when you have a law like P of x implies Q of x, you typically want to show that this always works. And to show that this works in one instance isn't that useful. So while the existential statements typically look like this is just one of several types of universal statements that we will look at here. So consider first a universal statement of the form, for all x in the universe, Q of x is true. That's sort of the complement, or I should say the counterpart to this one. But also consider a statement like this, for all x in U, if P of x holds, then Q of x holds. Now, though as I said, we could consider an existential statement like this, but it's more natural if something like P implies Q is always going to hold instead of just once as a fluke. There are several ways to prove such a statement. First of all, we could just try pure exhaustion. Especially works for something up here, but only if the universe is finite. If the universe is finite, we can just take each individual value of x and plug it in and see if Q of x is true. If it is, we're done. However, usually the universe is not finite. And in this case, we need a different method, such as a direct proof. Now this will work for both of these. In this case, we just let x be an arbitrary element, and we somehow prove logically that P of x implies Q of x. If we're in this case, or if we're up here, we just prove logically that Q of x has to be true. And of course, these are not the only two cases. We could come up with something more complicated, such as if P of x implies Q of x, then R of x is true, or R of x implies S of x, or we could chain these together with more layers. But these are probably the two simplest and most common cases. The third method is a type of indirect proof, which is showing the contrapositive. And here we really have to be talking about something like this, because the contrapositive of an if-then statement, if P then Q, is showing that if Q is false, then P is false. And that doesn't really make sense in this first case when we don't have any sort of implication that we're trying to prove. We're just trying to show that Q is true. So in this case, as before, we let x be arbitrary, but we're showing that not Q implies not P. And finally, we could try an indirect proof by contradiction. Now this should work for either of these. And in both cases, we assume that Q of x is false, which means that it just has to be false for at least one x. And we need to find a contradiction. So up here, the contradiction might be of the form that 0 equals 1, or that 5 is composite, or something absurd like that, in which case we are done. If we are down here, we could find a similar contradiction, or we can also maybe, if we assume that P of x is also true, as we should, we could possibly come up with the result that P is also false, in which case we have that P is true and P is false. So a proof by contrapositive we can always just rephrase as a proof by contradiction. Sometimes it's a little wordier and so not as elegant, so we try to do this if we can. But other times contradiction is just the easy way or really the only way to go. And we will see examples of both of these. But before we do, I will show you what the examples are, one by one for each of these cases. And as a thought experiment, we will think about how the method is going to go. So first, for all n, integers n, from 0 up to 40, I claim that n squared minus n plus 41 is prime. Now there's really no logical reason why this should be true, but it just happens to be true, sort of by dumb luck. So we really just have to plug in each of these values and check it. So this is an example of something by exhaustion. And also notice that this is clearly false for n equals 41, because 41 squared minus 41 plus 41, 41, equals 41 squared, and that is certainly not prime. Next, for all integers n being odd implies that n squared is odd. So this is something that we can prove directly. We can say that if n is 2k plus 1, we can show that n squared has to be 2 times some other integer plus 1. Our third example, for all real numbers, if r is rational and s is irrational, then r plus s is irrational. So it's, as I said in the previous lecture, it's hard to prove that something is irrational because we have to show that it cannot be written as a quotient a over b. So it's more natural to assume that r plus s is rational, and then we can explicitly write r plus s as a over b, and then we can prove that these two things both can't be true. So remember, if this is false, then at least one of them has to be false. And finally, here's a statement of this first form. For all primes p, there is a larger prime q. So this is just a way to phrase the theorem that we've actually already seen proved, that there exist infinitely many primes with a universal quantifier. And finally, recall that to disprove a universal statement, it suffices to find just one single counterexample. And we will do some examples of that after we prove these on the next slide. Okay, here we go. The first statement. I'm not going to actually check this for all 41 cases, but I just want to point out that this is something that is not true by any reason or any axiom or laws of logic. It's just true because we have a small enough set. It's just by dumb luck it happens to be true for these first 41 numbers. And you could ask, are there similar properties about numbers that are true for the first 1,000 numbers, or the first 10 million numbers, or the first 10 to the 10 to the 10 to the 10 to the 10 billion numbers? And there probably are things like that. Now you can go one further, or a lot more than one further. You could ask, are there properties that just by dumb luck happen to be true for all integers without any sort of logical axiomatic reason? And the answer to that is also yes. This was something that was proven by Kurt Gödel, a German logician in the early 20th century. And he showed that in any axiomatic system, there will be things that are true. Well, there will be statements that lay outside of the laws of logic. So in other words, they are not false, but there's no way we can ever prove them to be true. So there are not counterexamples, but these things are unprovable. And there are some actually very famous mathematical conjectures that are very easy to state about things like prime numbers that we have no idea how to prove. And a lot of people think that there's a good chance that these things are unprovable. In other words, they are not false, but it is literally impossible to prove them. So you and me would probably say, well, those things are true because there is no counterexample. But a logician is going to say it's not true nor false. Because remember what true means? A true is something that is something, a proposition is true if it can be deduced from a set of premises in finitely many steps. If you can conclude that it is true. And if you can't conclude that it is true, then it's not true, but it's not false either. So this turned the world of mathematics upside down when it was discovered in the early to mid 20th century. So more on that later. I'm going to actually show you one of these theorems that might be unprovable at the end of this lecture. Our second example is for all integers n, if n is odd, then n squared is odd. So this is probably easiest to do directly. Let's see how that's going to work. So if n is odd, then let's suppose, well, let's write that down. Suppose n equals 2k plus 1 for some integer k, then n squared equals, let's just write it down, 2k plus 1 squared, which is 4k squared plus 4k plus 1. And hopefully you can see that this is odd. And well, let's see, why is that? Because this is 2 times some integer, namely 2k squared plus 2k plus 1. So it is 2 times an integer right there, plus 1, so it is odd. Now we could try to do this using the contrapositive, but I think that looks a little bit harder. So let's think about what that would entail. That would be showing that if n squared is not odd, if n squared is even, then n is even. And we've seen something like that. We saw that if 5n squared plus 2 is odd, then n is odd. So it seemed to be harder when we went from something bigger being odd to something smaller being n being odd. So to actually prove this one, remember we did the contrapositive. We showed if n is even, then 5n squared plus 2 was even, and that fell right out. So similarly, this is just easier to prove directly than it is indirectly. However, the next two examples are easier to prove indirectly. So 3 says, if r and s are real numbers, or for all real numbers r and s, if r is rational and s is irrational, then r plus s is irrational. And now, why is this hard to prove directly? So r plus s being irrational means that there does not exist integers a and b such that r plus s equals a over b. And it's hard to prove that there does not exist integers. The standard way to do it is to show that suppose there are integers a over b, and then try to come up with a contradiction. But if you're doing that, you are doing an indirect proof. So let's do an indirect proof. Let's suppose that this is false. Let's show that this is false. Now, to show that two things are this and this are false, you just got to show that they're both false. We just have to show that one of these things is false. And so I'm going to rephrase this slightly, and then I'm going to prove that rephrasement, whatever the word for that is. So I'm going to rephrase 3 as let r be equal, or sorry, let r be a rational number. Then if s is irrational, that implies that r plus s is irrational. So sometimes it's just easier to rephrase things. And it's easy to see that this is equivalent to this. Okay, so let's prove the contrapositive. Let's prove that if r plus s is rational, then s has to be rational. So let's see. So let's let a or r be equal to a over b, because we know that r is rational. And then if and then suppose that r plus s is rational as well. So r plus s, say, is c over d. Okay. Then r plus s, so that means a over b plus s equals c over d. So we can solve for s, and we get that s equals c over d minus a over b, which is bc minus ad over bd, using basic fractions. So that is clearly rational, and b and d have to be non-zero. I didn't say that, but I think it's understood. So this proves the contrapositive, and therefore the implication is true. So I think it's fine to just say, put an end of proof box right there. Now, as usual, when we prove something with the contrapositive, we could instead do it via contradiction. So we could assume that r is rational and s is irrational, and that this is false, so that r plus s is rational, and then conclude that s is rational, and that would be a contradiction because we had assumed that r is irrational. So we can't have s or s. S cannot be rational and irrational and rational both. But that's just more complicated than it has to be. It's just cleaner to do the contrapositive instead of by contradiction. And it usually is if you have a choice. Remember that you have a choice when you have something like if this, then that. But our last example here is something that we've seen before. This is clearly equivalent to there are infinitely many prime numbers, which we've proven. But there's no implication here. So there's no if A then B. So it just says for all primes P, there is a larger prime Q. So directly we would have to, how are you going to cook up a Q? Find a formula for a Q. So indirectly is what we have to do, and there we basically have to do a proof by contradiction because we don't have an A implies B statement. So even though we've done this before, I'm going to do this, or I think we've done it before, and I think we'll do it again as well, but I'll do it really quickly. Let's suppose this is false, and then this means that there are finitely many primes P1 up to Pn. Now, if you're fine stopping here because we've proven that there are infinitely many primes, that's fine with me. However, if you want a refresher of why this fails, or why this is absurd, so I'll just put it here as a side note. Or maybe you are jumping into this lecture and have not seen the previous ones. Why are there infinitely many primes? In this case, let n be equal to P1, plus P1 times P2 all the way up to Pn. So take the product of these and add 1. And then this number here is not divisible by any of these prime numbers. So it has no prime factors smaller than itself. So it has to be prime, and that is a contradiction. So I'm not going to write that down. I'll just put this down as a hint and let you finish it if you want to, or you can refer to a previous lecture where this came up, and I think it'll come up in a future lecture as well. I don't remember offhand, but it's a classic proof there are infinitely many primes. Okay, so moving on. Next up, we'll talk about disproving universal statements. So as an example, let me take you back to the 1600s. Pierre Fermat, a French mathematician, came up with the so-called Fermat numbers. And these are defined as follows. Fn is the nth Fermat number, and it is 2 to the 2 to the n plus 1. So Pierre Fermat, as legend has it, was famously vain and would name things after himself. I don't know if he named this after himself or if it just caught on because he was the first one to define and study them. The first few of these are easy to compute. So the 0th one is 2 to the 2 to the 0 plus 1, which is 2 plus 1 equals 3. The first one is 2 to the 2 to the 1 plus 1, which is 2 squared, which is 4 plus 1, which is 5. The next one is 2 to the 2 to the 2 plus 1, which is 2 to the 4th, 16 plus 1, which is 17. And the next one is 2 to the 2 to the 3 plus 1, which is 2 to the 8th, 256 plus 1, which is 257. And then we have 2 to the 2 to the 4th plus 1, which is 2 to the 16th plus 1. And then we have 2 to the 2 to the 5th plus 1, which is 2 to the 32 plus 1. And that's this number here, which is, let's see, that's 4.29 billion. Fermat looked at these and said, well, these all look like prime numbers. 3, 5, 17, 257, 65537, and well, that one looks like it's prime. It probably is. It doesn't have any obvious factors. So he made the conjecture that, well, this pattern must continue because it's true for the first 6. All the Fermat numbers are prime. Sure enough, 82 years later, Euler, one of the most prolific mathematicians in history, disproved Fermat's conjecture by demonstrating that the 5th Fermat number, 2 to the 5 plus 1, recall that's just 2 to the 32 plus 1, or 4.29 billion, factors as 641 times, what is this, 6,700,417? Now this is almost laughable in today's standards because this could be checked in a split second via a computer. But of course this is hundreds of years before computers existed. And I don't know whether Euler just went one by one trying to find a prime factor until he found one, or if he had some more sophisticated way to do this. But sure enough, this is not a prime. So this disproves the universal statement that, which using our notation, we could say the conjecture was for all integers n, for all maybe natural numbers n, Fn is prime. So that is false because there exists a single counterexample. As it turns out, there's not just one counterexample. In fact, every Fermat number is known to be composite up to F32. And actually a lot more are known to be composite as well. In 2014, a computer helped show that 193 times 2 to the power of 3,329,782 plus 1, I don't even want to guess how many zeros that has, that is a prime factor of the 3.3 something millionth Fermat number. That is 2 to the 2 to that 3.32 million number plus 1. And this is, well, it's bigger than 10 to the 10 to the 10 to the 6th. That tells you how many zeros it has, but honestly, I can't even comprehend how many zeros this has. So that doesn't help too much. Now, it's not known that, well, that means that this Fermat number is composite. It's not known that everything up until here is composite as well. We just know some special cases due to some advanced number theory. But it is actually not known if any other Fermat numbers are prime. So Fermat in 1650 said, hey, look, F0, F1, F2, F3, F4, all prime? Maybe they're all prime. We haven't even found one more prime. And there's a very good chance, if you ask the number theorists, they tell me that it's probably the case that there aren't any more. That said, we are getting into that land of where that might be true for a reason. We might be able to prove it one day, but it also might be one of those statements that, well, there are not any counterexamples by dumb luck, which means it could, in theory, be undecidable. In other words, I would say it's true, you would say it's true, a logician would say it's not true because it's not provably true. We'll conclude this lecture with some so-called conjectures involving universal statements. Not all of these are going to be unknown, though. Like this first one we've seen, the number n squared minus n plus 41 is prime for all integers at least 0. We know that is false, so it's true for the first 41 integers, but it clearly fails if you plug in 41. Our second conjecture, due to Euler again in the 18th century. So he thought that there were no integer solutions to the equation a to the 4 b to the 4 plus c to the 4 equals d to the 4. So in other words, for all integers a, b, c, d, that a to the 4th plus b to the 4th plus c to the 4th does not equal d to the 4th. So to disprove this, all you have to do is find one single counterexample. But Euler was a smart guy. He knew that there were no solutions to a to the 4th plus b to the 4th equals c to the 4th. And while it in theory is easier to get something like this to be true when you have more things to work with, he thought it was unlikely. So this is, of course, a special case of Fermat's last theorem. There's Fermat again, which was that a to the n plus b to the n equals c to the n. Can only happen if n is less than or equal to 2. So there are no solutions when n is bigger than 2. That was not known in Euler's time, but it was known for many special cases, including this one here. So this was Euler's conjecture, perfectly reasonable. He certainly wasn't able to find anything, didn't have a computer. So when computers came around, not long after, in 1987, it was proven that this is false because it came up with a counterexample. 95,800 to the 4th plus 217,519 to the 4th plus 414,560 to the 4th equals 442, 481 to the 4th. So something that Euler never, ever would have come up with. I don't know if this is the smallest counterexample, but it goes to show you that some of these statements that look to be true, the counterexamples are very, very large. And you can ask, how big does a counterexample have to be? Because if some statement is true for every number up to 10 to the 10 to the 10 to the 10, we can keep going to the 10 to the 10 to the 10, that's a huge counterexample by human standards, right? Because that's bigger than us as humans can really comprehend. But there's infinitely many numbers. This is just as close to 0, or just as tiny of an integer as a 3-digit number in the whole scheme of things. So there's probably many theorems out there, or statements that we think are true, but are false. And the smallest counterexample is something of this magnitude. So this, to us, in 2019, and probably in all of humanity, is like what this was to Euler. The counterexample was out there, but there's just really no way to find it. And we're never going to prove it true if there is a counterexample. So we don't know if some of these conjectures that I said may or may not be unsolvable, if they really are unsolvable or unprovable, or if they are false, but we will just never ever find a counterexample. And that brings me to the famous Goldbach conjecture from the 18th century that I had promised earlier in the lecture. It says that every even integer greater than 2 is the sum of two prime numbers. This has been checked and verified for, well, n up to 4 times 10 to the 18th, which is a pretty big number unless you're looking at the whole scope of positive integers, in which case we haven't even scratched the surface. So once again, we really have no idea whether this theorem is true and is provable, or whether it is true and unprovable, or in other words, not true, because it can't be proven, or whether there's a counterexample that is so big that we will never, ever discover it. And that brings us to the end of this lecture. Our next lecture is going to be more about prime numbers and factorization. So if you like this, stay with us.